Hello and welcome to this lecture on regression. After this lecture, students should be able to describe linear relationships and prediction rules for bivariate and multiple regression models, construct and interpret straight line graphs and best fitting lines, calculate and interpret A and B, the constant and the slope of a linear regression equation, calculate and interpret the coefficient of determination in Pearson's correlation coefficient, and interpret multiple regression output. Let's go over some regression terminology. Correlation is a measure of association used to determine the existence and strength of a relationship between two or more variables. It is similar to proportional reduction of error measures from last week. Regression is a linear prediction model that uses one or more independent variables on a single dependent variable. A bivariate regression is a regression model with one independent variable and one dependent variable, whereas multivariate regression or multiple regression is a regression model with two or more independent variables and one dependent variable. Again, it's also sometimes called multiple regression. Regression models, particularly linear regression models, are an example of what we would call a linear relationship, where we take a scatter plot, a plot of a bunch of different data points, and try to fit what is called a best fit line. And the line drawn here in this graph is a straight line that attempts to minimize the error between the line and each individual data point on this scatter plot. So you have a bunch of data points, and the goal is to draw a line that best fits those data points such that the average or mean error is minimized. And this equation can be stated as y, our, in this case, dependent variable, is going to be equal to a, our constant, plus b, our slope, times our independent variable. If this were a deterministic relationship is a relationship between two interval ratio variables in which all observations fall along a straight line such that the independent variable will perfectly predict the dependent variable. This is not the case here. We can see that some of the data points do not fall directly along this line. However, this line is an attempt to best fit this data. So a bit more about this equation. Again, it's going to be y equal a plus b times x. Again, where y is the predicted score on the dependent variable. A is the y-intercept, where the line crosses the y-axis, or the value of y when x is 0. So it'd be something over here. This is 10, but if we drew our temperature here to 0, that intercept point would be over here. B is the slope of the regression line, or the change in y with a unit change in x. So for every degree that temperature changes, the sales would increase by y, or by b, excuse me. And so x is the score on the independent variable. So for every change in x, again here it's temperature, we'd expect the change in sales to be equal to b. That is why it's temp b times x. The best fitting line is the one that generates the least amount of error. There's still going to be some error. We can see all these red arrows pointing to the error that we're going to have. As you can see, some of these data points are further away from the line than others. These are called residuals. And these residuals are the error that arises from our predicted values from our best fit line not quite matching up with our data points. This error is calculated for each data point as follows. E, the error, is going to be equal to the data point y, the actual data point, minus our prediction for y. So using these residuals, we can calculate what is called residual sum of squares, and this is a overall measure of the amount of error we have when we add up all the differences between our individual data points and the data points predicted by our equation, by our regression equation. So we need to add these all up. Unfortunately, because of the way regression works, we can't just add them all up. And that is because if we added them all up, if we just added all the differences between each point and the prediction from the line, we would get 0. Because with the best fit line, it's creating a mean prediction, which means that if we add up all the differences between a mean and each data point in a data set, we are going to get 0. And so if we chose to do it just adding them up, we would get a residual of 0 for the whole equation, which isn't correct. We know that we have some error, so getting a total amount of error of 0 wouldn't make sense. So what we do is we square it. And so when we calculate our residual sum of squares, it's going to be the sum of each one of those individual data points minus our predicted value from your equation squared, and we're going to add each of those up. Minimizing the residual sum of squares requires finding the least squares line or the best fit line. To do so, we will use the least squares method. First, we will calculate a, our constant, and b, our slope. B is going to be equal to s sub xy, where s sub xy is the covariance of x and y. S sub x is the variance for x, the independent variable. Y bar is the mean of the y for the dependent variable. X bar is the mean of x for the independent variable. A is the intercept, and b is the slope. So these are the equations we're going to use in order to find that best fit line. So let's talk about calculating those variances and covariances. The variance for x is calculated like we would most variances. It's going to be the sum of x minus the mean for x squared. And we're going to sum all those up, divided by n minus 1. Remember that x is the individual data points for our independent variable, and x bar is the mean for our independent variable. The covariance for x, y, so for x and y combined, is going to be the sum of x minus x bar times y minus y bar divided by n minus 1. Once we have these, we can plug them into our equations for a and b and calculate those out. As you can imagine, if we had a very large data set consisting of hundreds or even thousands of data points, this sort of mathematics will become very tedious, as we have to do that for thousands and thousands of data points for both our independent and dependent variable. The linear regression equation of y equal a plus b times x is good for determining both the slope and the effect of the independent variable, but it doesn't really tell us how much of the independent variable and dependent variable we are actually explaining, or how much the independent variable is explaining of our dependent variable. And so in order to get an idea of how much of our dependent variable we are actually explaining, we use something called the coefficient of determination, or R square. R square is the proportion of the total variation in the dependent variable that is explained by changes in the independent variables. In other words, how much does education explain the variation in incomes across different people, would be another way of saying that. And we're going to calculate this using the following equation. So this equation says that our R squared, or coefficient of determination, is going to be equal to the covariance for xy divided by the standard deviation for y, and the standard times the standard deviation for x. So let's practice interpreting some regression. Let's look at the following equation for years of education and income, where y is income and x is years of education. We have y, again income, is going to be equal to 30,000, our constant or a, plus 2,000 times x, where 2,000 is going to be our slope, or b, and x is going to be our independent variable. So again, y is the dependent variable, 30,000 is a, our constant or y-intercept. This is where your income would be if you had 0 years of education. So you can see that y would equal 30,000 plus 2,000 times 0. And so if you had 0 years of education, you would have $30,000 in income. The slope is 2,000, so that means for every year of education, your income on average will increase by 2,000. And we can see this calculated out. If you had 2 years of education, your income is going to be equal to 30,000 plus 2,000 times 2, which is going to be 4,000. And so you'll have an income of 34,000. If, for example, you had 10 years of education, then you'd have 30,000 plus 2,000 times 10, which is going to be 20,000. And so your yearly income would be 50,000. And we could keep going on up in this sort of way to find out if you had, say, 15, 16, 17 years of education, what your income would be. However, it's likely that education is not the only explanation or only variable that could explain your income. Things like the type of degree you have, where you live, how much income your parents had, etc., probably have more to do or as much to do with your income as just your years of education. And so we may want to add those variables to our model in order to account for things like parental income, degree, where you live, etc. And this adding of variables that might relate to our relationship between our independent and dependent variable is called elaboration. Elaboration is the idea of adding more independent or control variables to your model. This allows you to control for extraneous variables that might impact the relationship between our variables of interest and also increase our correlation coefficient, or R squared, to explain more the variation in our dependent variable. And it might look something like this, where our predicted value of y is going to be equal to a plus b1 times x1, so the slope for our first independent variable times the value for our first independent variable, plus b2 x2, second independent variable slope and variable, b3 times x3, third independent variable slope, times third independent variable, so on and so forth. All right, we're going to end with a little summary of all the variables here. Please let me know if you have any questions. Otherwise, thank you for watching, and I will talk to you next week.